The second method to find the time complexity of any piece of code is to consider all the loops in the code. Consider the following examples. We have already seen an example where a for loop is executing constant number of times. So if a for loop is executing constant number of times, then the time complexity of this for loop will be constant. It does not matter whether this constant is big or small. Even if this constant is 1 or this constant is 100 or this constant is 1000 or 10,000 or 100,000, the time complexity will still be constant. Because by definition, the asymptotic time complexity is the time taken when the input size is very large, when n tending to infinity. So when n tends to infinity, then any constant plus n. So if I say n plus 100, if the value of this n is 100, then 100 plus 100, so it will double. So adding 100 to a value which is also 100 will double the value. So it's a significant improvement. But if you add 100 to a value which is say 1 million, then 1 million plus 100 will be a very minuscule improvement over 1 million. So what if n tends to infinity? When n tends to infinity, then infinity plus 100 is also infinity. So this 100 will essentially stop contributing in the value of n. So that's why we ignore all the constants when computing the asymptotic time complexity. We have also seen that if a for loop is executing n times, then the time complexity of this for loop is order of n. You can replace this for loop with a while loop and the time complexity still remains the same. So it does not matter whether it is a for loop or a while loop, we essentially consider the number of times a particular statement is getting executed. So in the subsequent examples, even though we have taken for loop, you can very well replace it with a while loop and get the same time complexity. We also saw that if I is incremented by a constant number, if we start with I is equal to 0 and the increment is I is equal to I plus 2, then also this for loop will be executed n by 2 times and n by 2 is on the order of n. So that's why this is also big O of n. Instead of doing I is equal to I plus 2, if it is I is equal to I plus 10, which means that we are incrementing I by 10, then also the time complexity remain order of n because n by 10 is also big O of n. Therefore, whether we are incrementing by 10 or 100 or 200 or 300 or 150, it doesn't matter. As long as the number of times the for loop is getting executed is a linear function of n, the time complexity remains big O of n. But what if we increment I by n by 10? So every time when we say I is equal to I plus n by 10, we are saying I is equal to I plus 10. If value of n is 1000, then we are saying I is equal to I plus 100. If value of n is 10,000, then we are saying I is equal to I plus 1000. Now this increment in I is not constant. And we can conclude that this for loop is getting executed 10 times. Therefore, the time complexity of this for loop in this case is order of 1, which is constant. What I'm trying to say is that you should focus on the number of times the loop is getting executed instead of the variable. We have also seen the case of doubling and halving. We have seen that if the counter variable is doubling every time, then after log n iterations, it will be able to reach the value of n. Initially, I is 2. Then in the next iteration, the value of I will become 2 square. In the next iteration, value of I will be 2 cube. In the next iteration, the value of I will be 2 raised to the power 4 and so on. We will stop when 2 raised to the power k becomes greater than or equal to n, which means that k becomes greater than or equal to log of n to the base 2. So the total number of times this for loop is getting executed is k. Therefore, the time complexity of this for loop is order of k. The same is true for this for loop also. The time complexity of this for loop is also order of k. Here also we are just doubling I. So it is just a matter of how we are writing it. In both the cases, we are doing I is equal to I plus 1 or I is equal to I into 2. What is true for doubling is also true for halving. So here we start with I is equal to n. And in the next iteration, the value of I will be n by 2. In the next iteration, the value of I will be n by 2 square and so on. So we keep on reducing I till n by 2 raised to the power k becomes less than 1, which means that 2 raised to the power k should be greater than n, or k should be greater than log n to the base 2. So because the loop is iterating k times and k is greater than log n, so this loop is getting executed log n times to the base 2. Therefore, the time complexity of this for loop is big O of log n to the base 2. We have seen in the previous section how doubling the loop variable result in exponential increase of that variable, which means that that variable will be able to reach the destination much faster, and that variable will reach the destination in log n steps instead of n steps. How about the case when I is incremented as I into I square? So in this case, I is initially 2, then we square I. Square I means it will be I square. Then we square this. It means that I square square. And we keep on doing it in every iteration. Therefore, after k iterations, the value will become 2 raised to the power 2 raised to the power k. We will stop when this value becomes greater than equal to n. If you take logarithm on both the sides, 2 raised to the power k is greater than equal to log n to the base 2. This implies that k should be greater than equal to log of n. In both the cases, the base of the log is 2. So here also and here also. It means that this loop is iterating k times, where k is equal to log of n. Therefore, the time complexity of this for loop is big O of log of n. When I'm not writing the base, it is assumed that the base of the logarithm is 2. What if I is getting reduced to the square root of I after every iteration? So initially I is n, then after the first iteration the value of I will be square root of n, then after the second iteration the value of I will be square root of n, which means n raised to the power 1 by 4. In the next iteration the value of I will be n raised to the power 1 by 8, which is 2 cube. In the next iteration the value of I will be n raised to the power 1 by 2 raised to the power 4, and so on. After k iterations, the value of I will become n raised to the power 1 by 2 raised to the power k. We will stop when this value becomes less than 1. So we will stop after k iterations only if this condition is true. If you take log on both the sides, 1 by 2 raised to the power k, log of n to the base 2 is less than 1. I am keeping it 1 because log of 1 is constant. It means that 2 raised to power k is asymptotically equal to log n to the base 2. Don't get confused by this greater than sign and this equal to sign, because we are dealing with asymptotic complexities and not the exact mathematical equalities and inequalities. It means again that k is equal to log of n to the base 2. So even this for loop gets executed log of n times. It means that the time complexity of this for loop is again big O of log n. Now let us see some examples where the loop is nested, which means that we have one loop inside the other loop. We are showing the for loops here, but this can be a combination of while loops also, or it can be a mix and match, that the outer loop is a for loop and the inner loop is a while loop, or the other way around. We have already seen that if the outer loop is getting executed n times, and inside this loop if the inner loop also executes n time, then the time complexity of this entire for loop is order of n square, because the statements inside the inner for loop gets executed order of n square times. So that's why the time complexity of this is order of n square. If the inner loop is executed m times, then the time complexity will be order of m into n, or n into m, whatever you call it. If there are 3 loops, then the time complexity will be order of n cube. If the outer loop is iterating n times, the second loop is iterating m times, and the third loop is iterating p times, then the time complexity will be big O of m into n into p. If all of these 3 are same, then it will be n cube. So the thumb rule in case of nested loops is that find the number of times the outer loop is getting executed. Let's say the outer loop is getting executed x times, then find the number of times the inner loop is getting executed for every iteration of the outer loop. Let's say for every iteration of the outer loop, the inner loop is executing y times, and there are only 2 loops, then the time complexity will be x into y. If there are 3 loops, then find the number of times the third loop is getting executed for every iteration of the second loop. If the third loop is getting executed z times, then the time complexity will be x into y into z. But sometimes the number of iterations of the inner while loop is not constant. Consider this case. The outer loop is executing n times, and for ith iteration, the inner loop is executing I times. And this I will keep on changing for every iteration of the outer loop. In this case, we have to use the summation method. The summation method is that find the number of times the inner loop is getting executed for every iteration of the outer loop, and then add all of those numbers. For example, when I is equal to 0, the inner loop executes 0 times. When I is 1, the inner loop executes 1 time. When I is 2, the inner loop executes 2 times. When I is 3, the inner loop executes 3 times, and so on. When I is n minus 1, then the inner loop executes n minus 1 times. Therefore, the total number of times this particular statement gets executed will be a summation of all of these. which is summation of n minus 1, that is order of n square. Therefore, the time complexity of this nested loop is also big O of n square. Consider another case. In this case, the outer loop is getting executed n times. And we know that the inner loop is getting executed log n times to the base 2. Therefore, we can conclude that the total time complexity of this entire piece of code is n into log n to the base 2. If the outer loop is getting executed log n times and the inner loop is getting executed n times, then also the time complexity will be n log n. If the outer loop is getting executed n times and the inner loop is getting executed n square times, then the time complexity will be n into n square, and so on. This function sorts the given array using insertion sort algorithm. Now how it works is, let's say the array given to us is 5, 3, 4, 6, 1. If we want to sort this array using insertion sort algorithm, what insertion sort does is that it divides the array in two parts. This is the first part and this is the second part. First part is the sorted part and second part is unsorted part. Every time it takes one element from the unsorted part of the array and insert it in the sorted part of the array. First it will pick 3, then insert 3 at the right place in the sorted array. So the sorted part will become 3, 5. Then it will pick 4 and insert it at the right place in sorted part of the array. So the sorted part will become 3, 4, 5 and so on. So we'll consider all the elements starting from second element of the array. That's why this outer loop starts from I is equal to 1 instead of I is equal to 0. So initially I is here. Then we move this I in some temporary variable. So temporary variable is 3 now. This position practically becomes empty. J will start from I minus 1, which means J will start from this position. The inner while loop will shift all the elements which are greater than 3 one place forward. So 5 will be shifted here and the position of 5 becomes empty. At the end, when this while loop is over, then 3 goes at the empty position. This is how the sorted part of the array increases and the unsorted part of the array decreases. Now the length of the sorted part of the array is 2 and there are only 3 elements in the unsorted array. Next element to be picked is 4. So temporary variable becomes 4. The position of 4 becomes empty. J will start from I minus 1. Because 5 is greater than 4, so the while loop will iterate and 5 will be shifted one position forward. Then we will consider 3, but because 3 is not greater than 4, so we will move out of this while loop and 4 will be placed at the empty position, which is here. Now the array has become sorted up to 5. In the next iteration of the for loop, we will pick 6. Now the temporary variable is 6. The position of 6 becomes practically empty. J will start from 5 and it will move all the elements which are greater than 6 one step forward. But because 5 itself is not greater than 6, therefore we will not enter the while loop even once and 6 will go at the same position where it was. Now for the last element 1, temporary variable will be 1 and all the elements which are greater than 1 will be shifted one step forward. So 6 will come here, 5 will come here, 4 will come here, 3 will come here and 1 will move at the very beginning of the array. You may notice that the outer for loop is getting executed exactly n-1 times. But the number of iterations of the inner while loop depends on how many elements need to be shifted for this particular element which we want to insert in between. In the worst case, this while loop can get iterated I times because all the I minus 1 elements will be shifted. And in the best case, this while loop may not get executed even once, which means that it will be iterated only 0 times. So in the worst case, the time complexity of insertion sort can go up to n square, whereas in the best case, it will remain order of n, which is the time complexity of the outer for loop, because the inner while loop is not getting executed even once. This best case time complexity will come when the array is already sorted. So if the array is already sorted, it will be 1, 2, 3, 4, 5. For 2, nothing need to be shifted, so we will not enter this while loop. For 3, again, nothing need to be shifted, so we will not enter this while loop. For 4 also, we will not enter this while loop, and for 5 also, the execution will not go inside the while loop. So the execution will never go inside the while loop, and the total time complexity of insertion sort will be order of n, which will be the complexity of the outer for loop. But if the array is sorted in reverse order, let's say we want to sort the array in ascending order and the array given to us is sorted in descending order. Then for 4, 5 need to be shifted. For 3, both 4 and 5 need to be shifted. For 2, all of these 3 elements need to be shifted. And for 1, all the previous 4 elements need to be shifted. Therefore, the time complexity will be big O of n square. So sometimes the best case and worst case time complexities are different. However, the asymptotic notations as such are not related to either the best case or the worst case. This we have discussed in the previous section. What if we have more than one loop and those loops are spread across multiple functions? Let's say we are given a two-dimensional array and we want to print all the elements of this two-dimensional array. One way of printing all the elements of this two-dimensional array is to have two nested loops. For row is equal to 0 to n minus 1 and for column is equal to 0 to n minus 1, print that particular row and column. Let's say we have divided this in two separate functions. This function print row will receive a row as parameter and it will print only that particular row. So it will print all the columns of that row. If row is 0, then first it will print this value, then this value, then this value, then this value, and then it will stop. If the row is 1, then it will print all the elements of the first row. If the row is 2, then it will print all the elements of the second row and like that. What the print matrix function does is that for every row, it will call this print row method. So for row starting from 0 to n minus 1, it will call the print row method. Now let us look at the time complexities. It is fairly simple to say that the time complexity of print row function is big O of n, where n is the number of columns in a row. What about the time complexity of print matrix function? The print matrix function has this for loop. This for loop will execute n times. Inside this for loop, we are calling the function and this function takes n times itself. So the total time taken by the entire print matrix function is n times n, which is order of n square. So this is order of n square function. You may have noticed that it is no different from having nested loops. In case of nested loops, we count the iterations of the inner loop and then count the iterations of the outer loop. In this case also, we find the time complexity of the inner function and the time complexity of the outer for loop inside which the inner function is getting called, and then multiply the two. What do you think is the time complexity of this code? There are two functions. One is the print one line function. So this function is responsible for printing only one line. In this line, it is printing k stars. Therefore, the time complexity of this function is order of k. The second function, print stars, is calling this function. Now we need to figure out how many times this while loop is getting iterated and what is the value of k for which this print one line function is getting called inside the while loop. In the while loop, n is getting halved every time. If the initial value of n is, let's say, 32, in the next iteration the value of n will be 16. In the next iteration n will be 8 and so on. It means that this loop will get executed log of n times to the base 2. But this is not enough because the print one line function is not being called for constant value k, which means that we are not printing constant number of stars in every line. In the first line, if we are printing 32 stars, then in the second line we are only printing 16 stars. Then in the next line we are only printing 8 stars. So how many stars are getting printed in total? Let us see for what values of k this print line function is getting called. First, the print line function will be called for n. Then the print line function will be called for n by 2. Then the print line function will be called for n by 2 square. Then the print line function will be called for n by 2 cube and so on. The last value for which this print one line function will be called will be n equal to 1. Therefore, by the previous method, we can say that the total time complexity will be sum of all of these values. Now, how do you find the sum of all of these values? Now, this is a GP series and it's a decreasing GP series. As a thumb rule, you can remember that the sum of decreasing GP series is big O of the first term of the series. So here the first term of the series is n. The sum of this entire GP series is big O of n. If you want to compute it, you can also compute it. Just assume that the sum of this entire GP series is equal to t. Now, if you multiply both sides by 2, you will get 2t is equal to 2n plus n by 2 plus n by 2 square plus so on plus 1. Now, you will notice that this series is exactly same as this series, which is equal to t. This implies that 2t is equal to 2n plus t, which means that t is equal to 2n, that is big O of n. So this is how we can find the time complexity. Consider one more example. You may have seen this question that you are given an array and you are given a number k. You have to find whether or not a pair exists in the array with sum equal to k. If the given array is 5, 3, 8, 9, 2, 15 and the value of k is, let's say, 13, then the answer should be true because 8 plus 5 is 13. So a pair exists with sum equal to 13. If k is given to be 14, then the answer should be false because no two elements in the array will add to give 14. Now, one way of solving this problem is that for every element, you check whether the pair of this element exists or not, which means that for 5, we will be searching for k minus 5 in the entire array. This searching can be a simple linear search. So for every element starting from I is equal to 0 up to the second last element, we search in this array for value k minus ai. And if that search is true, it means that we have found a pair. Otherwise, we move to the next element. And if we do not find the pair in the entire array, then at the end we just return false. Now this outer for loop is getting executed n minus 1 times, which means that this is getting executed order of n times. And how much time are we taking inside this for loop? The time taken inside this for loop depends on the time complexity of this search function. Because this search function is a linear search function, takes order of n time, we can say that the overall time complexity is n square. But if somehow this linear search can be converted to binary search, then the time complexity will become n log n. Now you will say that how can we convert it to binary search because the array is not sorted? Maybe we can sort the array first and then get into this logic. The entire solution of this problem is out of the scope for this course, but you can see that if you apply binary search, then the time complexity will reduce to n log n. And if you use hash maps, then the searching will further reduce to constant time, and hence the time complexity will reduce to n. It will become a linear time function. Sometimes there are multiple loops, but those loops are not present one inside the other. If a for loop is followed by another for loop, then the effect will be additive and not multiplicative. Consider this function. This function print m stars and n hashes. So the total time complexity of this function will be m plus n and not m into n. Because first the first for loop will execute and then the second for loop will execute. The first for loop will take m time and the second for loop will take n time. And the total time taken will be m plus n. So this is how we find the time complexity when loops are present in the code.